Hey, thanks for coming. We're going to get started now. I'm Ryan, and I put together this session a few months ago, and it was originally just about some work we were doing at NCEI, but I heard from Thomas, who said, that it'd be really interesting to do a session on this as digital twin Earths, and it's a really interesting topic. To me, it's a bit of a buzzword, but it'll be really interesting to see what's going on. And please sign in. And then the schedule is Thomas will give his presentation, and then I'll give my presentation, and then we will take questions and hopefully get some good participation and look for future collaboration. So without further ado, Thomas.
Hi. Wait, this thing is really tall. Well, I'm really short. It's good to see everyone again after so many years. I was congratulating my friends here. I haven't seen them for 3 years and they haven't changed a bit. And Ken, thank you for opening this morning. I might get a little bit rusted because I haven't stood in front of the crowd. I had a little bit of a head start because I talked to a bunch of students a little bit, but their bar is lower. All right. So today I'm going to talk about the project called Digital Twin, Earth System Digital Twin. This is an effort that NASA AST is leading, Again, I just gave this very same talk about 2 hours ago for IGARs. Trying to figure out how it can be in 2 places at the same time, but I'd rather be here than in Malaysia. So anyway, the work is, as you can see, I have a large team of people, actually involve people from multiple centers and also people from another agency. Let me see here. Click. Sorry, I can't drive a PC. Okay. Thanks. Okay, so if you haven't been to the NASA AST or ESTO website, if you go there, you will find the definition. Is the definition for Earth System Digital Twins. So I know it's a buzzword, like Ryan mentioned earlier, but we do have a very specific definition because again, it's a different person you've talked to, they have a different understanding what digital twin is. But NASA ESTO offers the AST program, have a very specific definitions. That's involving is an interactive, integrated, multi-domain, multi-scale digital replica of the state and temporal evolution of the Earth system. So the goal is really not just creating numerical models or to try to mimic what the Earth is look like, but definitely the model is a very important piece. But on top of that, we need to be able to onboard new observation and be able to drive scenario-based predictions and actionable predictions. And so basically, if in a nutshell, the definition according to the NASA AST program is really to try to create an integrated end-to-end system that connects observation to model simulation, to machine learning, and to enable us to do things like estimating what's the possible damage or estimation, or what we'd be looking like, and what are the valuable data that we should be bringing in the next observation. Some of the key components that this is do the study working with the AST program that identify there's really 4 main components, right? One is the data and service assets, which is the big community here, looking at how to do ETL, onboard data transformation, harvesting, harmonization, regrading the data, transforming the data into cloud optimized or analysis ready data, right? That's the important part to getting the data onto environment. And then the second part is to the new observation analysis, means that using a smarter method to automate onboard new relevant data. So we don't just want to bring in any data, right? You want to be smart about what data to bring in. I mean, let's face it, we have a big data challenge, right? Everybody know that. It's not going to get any smaller, right? Actually, I asked Aaron one year, Robinson, in the conference, like, how do we make big data smaller? We can't, right? So the only thing we can do is be smarter about what to do, what kind of data to use, right? Integrating multi-physics, multi-scale, probabilistic models. We have lots of investment, lots of models out there, right? How do we get this model integrated with new observation, improve those model forecasting, and finally, AI-based analytics in terms of not just say, well, here, look at my machine learning model, but can we productionize ML, right? So that you can automate to give us not just say, well, this is what the plot looks like, but say, go send some people over there, or go to that the local river gauges, fetch the data from that location. If there's UAV, can we dispatch the UAV? If there's an orbital satellite, right, that actually has a retestable instrument, can we send uplink a request for schedule for the next observation? Actually, we are working with that. That's a dual-party air quality project. So I really love to be here because it's like, grab the picture, right? Digital twin, in my definition, right, should not be trying to move everything to the cloud, try to create one big platform, right? And I know somebody's like, what? The whole idea is bridges, right? Building connections, right? If not everything gonna run on the cloud efficiently and affordable, right? You have to be something say, hey, look at all this model can run on HPC, or they've already been tested many times. Why can't we leverage that, right? So building bridges to this, but being able to connect to different assets. So that's why it's not just one cloud, but it's actually multi-computing architecture. Be able to identify resources, be able to describe or discover the right resources, formalizing the interfaces between services, right? We have lots of different pieces, different program. NASA has different program building models. They have, the measures, and they have all this access and AIST. They build different focus area. We already have all these main working engines. Can we connect these things together, right? That's the whole point about digital twins. And I also provide some definition what digital twin Earth system is not, right? It's not just a model. It's also not a one-off. Digital shadow means you pull the data one time, run the simulation. It's like, well, look at this pretty picture I got. That's not enough. We want to do this full feedback, right? So about 6 months ago, we started this project under the ESTO office. It's called Ideas. And we are using water cycle and flood analysis as our prototype application. But as a computer scientist myself, I'm always trying to generalize the architecture, right? To not limit it to just for water. As a matter of fact, I already plan to use this for air quality. Here's the pitch. Go to my next session, 4 o'clock. So it definitely is on the roadmap for this, right? So if I put into if you look at the picture here on the right, it's really fill in the blanks. Where are the data assimilation, right? Where's the models, and where are these numerical or also machine learning predictions? And more importantly, this is actually a multi-agency effort because we're working with the CNES in French, and also the Space for Climate Observatory, SCO. So they are building a flood detection capability, which myself was working with them 2 years prior to do predicting flood at the Mississippi regions. And can we federate the solution to using some of their HPC capability, their processing power on the Sentinel data, and their flood risk map generation capability? Can we federate to them? They do that, and on them, they can federate pulling from us about our model in terms of water discharge or river discharge. Right? That's the whole point where this architecture comes in. Now, some people would look at say, well, besides bringing data, besides bringing model, right, there are also other things that you have to think about, like data. If anybody work on GDS, you will know data coming in is raw, right? They got They got what? The battery, compressions, engineering data, like we don't care about that. So this is just a connection to science data system where you have to do processing on it, right? So on demand processing, there's lots of effort. There's gonna be a great talk tomorrow, a session on MAP. My friends on MAP say, right? Go to that session. This is where the connection comes in. So all right. So the approach is we want to define the architectural and the interface and the workflow for the system. We also want to demonstrate how to do dynamic data retrieval and also integrations. And we also want to develop the machine learning capability for actionable predictions. That's the whole picture of this is the manager's picture. That's why I showed to my manager, because they like pictures. So, so you bring in data, harmonize them, right? You're creating one common platform and the cloud optimized for interactive analysis, visualizations, data access, subsetting, matchup, all that stuff. And then you will use that common cloud optimized platform to drive your simulations and also for your AI. So let's say run to SageMaker, retrain your model and deploy your model. Use that model to generate predictions, right? The prediction could be telling our decision maker, you need to, move your people off the coastline about, that far away, prepare for that in the next, 5 to 10 years. Or are there actually data that over at the gauges data that we should go hit, right? I think you all know that besides satellite data, which is already big data, in situ data is even bigger. There's so many little sensors going around. They collect data every, I don't know, 5 minutes, 30 minutes, depends which station you hit. It's impossible for us to bring all those data in from all the sensors across the globe. That's ridiculous, right? Why can't we use ML to decide which area that we should bring in for what time period? That's a smarter way to deal with big data. Not just say, well, maybe we're bringing in, somebody will use it, right? So ML is not just for prediction, but ML also should be used for resource planning and process planning, process management, right? Or you can use the ML for us is also being able to retest a satellite or drone. When you collect the data, you stage it somewhere where you can actually fetch it, or you can fetch it directly from the device like IoT. Okay, so again, I just started this talk saying that we don't want to move everything to the cloud. It doesn't make sense. As a computer scientist, I tell my students the same thing. It's just because I give you a hammer, don't treat everything as nails, right? You pick the right tool for the right problem, right? So this project is going to be integrating things in the cloud. We're going to integrating things from HPC because we have model simulations. We have things that's running on-prem, okay? How do you build bridges across all of them, right? As I prepared for this slide, I found the tutorial I gave at UC about 11 years ago on Introduction to Cloud, right? That's where Phil Yang over there in the back and I started the cloud cluster. And I asked the question, is this a silver bullet? And 11 years later, actually say, it's still not the silver bullet. Again, it depends, right? You pick this technology for the problem that you need to solve. So in this case, we are actually integrating, it's a multi-computing problem. It's a multi-agency effort between NASA and CNES. It's multi-center because it's actually involving at least 3 NASA centers. We are looking at standards, and especially the 4 that will be listed here, OGC, W3C, stack, and UMM. So big data is really being about smarter about data. Agility and also relevance, right? Means you have to be smarter. Being agile means that, remember, as ideals, we think about, hey, maybe we'll be able to have all the data in all time in one location. Well, reality is we don't, okay? This cloud sometimes blocks things, right? Satellite may skip a track. Can we build a system to figure out that based on the location, what kind of data is available for that location? That's what part of the DT I was looking at too, being smart about what data is relevant for the research that we're looking at. And we're not locking to specific programming language. Again, as a computer scientist, I know many languages. So we are federated digital twin because we're working as a building at NASA, what we're focusing on hydrology for the IDS effort. But the flood dam over in the Space for Climate Observatory, they're also building the similar effort on looking at the French region. So we just had a face-to-face meeting a couple of weeks ago when right after my Living Planet Symposium in travel, and basically formalizing the interfaces and data sets and how do we integrate between the two systems and formalize the use cases. So again, we're building not just an application, we're building as a platform, right? Somebody today's one of the keynote speakers looking at is like, we cannot just treat all the users the same, right? We have different kind of users. Well, don't just build one tool. Build a platform so you can build different tools on top of that, right? So, okay, so this is like example of that, right? This is actually the project that we built for sea level, where you run the tool on the desktop, but you also can run this on your iPhone. This is live running on the cloud, compute on the fly, no massive data transfer to your device, all low bandwidth. Okay, that's the key, right? I actually use this phone a lot more than the desktop because I sit in the airport a lot. So, but the whole idea here is minimize the data movement, leverage the platform, but the most importantly is that your user won't have to go take an Amazon class to use your stuff, right? I get overwhelmed every time somebody say you have to go take a class on this and this to do this. Well, I never had to take a class when I signed up for my Gmail account. It has to be that way, right? So this, not just a tool, but you can build, okay, as a platform, right? So, and people been to our sea level portal, it's the same technology, right? You would know that you have really lots of tool running there, but it's actually a platform. It's actually got APIs that you can talk to. You can use any programming language to compare the analysis between different tools. Using Jupyter Notebooks, you can use your MATLAB or IDL if you want. You don't have to learn a new language in order to work with the cloud, or you don't have to take a cloud training class just to use the cloud, right? If you want to, you can, right? I'm not taking that away from you, but as a computer scientist, I want to make things simple, right? Because my people were stuck maintaining it. So, all right, so federations, right? Building one big platform is great. Wouldn't it be great if you create a bunch of these platforms that's open source, open APIs? You can just, now everything's compute, could be on-prem, could be on the cloud, could be on your private cloud, on Amazon or Azure, whatever, but they're API based. Now you can use the Jupyter Notebook, you can actually talk to this system without having to go sign up an Amazon account, right? You can just compute time series here, compute time series there, generate your matplotlib on your Jupyter Notebook. Somebody's paying for that. And the main thing is sustainable and affordable because they already pay for the environment that's running. There's no auto scaling, right? That's what everybody's scared about. And therefore, and then you don't have to get all the security stuff, right? You just call the API and computation done it for you. So these are the charts that actually, on the right, it's actually some of the plot that was generated by this federated approach interactively without moving any data across different clouds or environments. And as a data geek like myself, right, we spend a lot of time doing data wrangling, data transformations. How many people have to do that? Everybody have to do that. When you run a proposal, you have to transfer, like grab the data in, regrid the data. It's like, why? You do the same thing. How many times you have to do this for sea surface temperature data? It's like, it's the same data, right? Well, if you have a service that's already been optimized for that parameter, just call the damn API. So immediately focus on the analysis and not spending time doing data wrangling, right? So that's the whole point. So besides the whole data optimized platform, we're also integrating with the land information system in Goddard, right? They are the one that actually runs the simulation for runoffs. Okay, so obviously, if you think about flood, it's usually things about runoff, river discharge, and extents, right? And change the depth of the water. So we need that close loop. So we are building a bridge with the LIS. LIS is running on NCCS on Goddard, their HPC environment, right? They are trying to move to the cloud. That's fine. Moving to the cloud is just a step. Can you pay for it? That's the big question, right? Does it make sense to run a big simulation on a cloud? Maybe not. It's maybe too expensive to do. It's good to show a demo, but my bar to my engineer is that, great, show me, but how do we sustain this? Can we afford this? I can show you I can do some number crunching in fraction of a second, but it's going to cost you a lot of money. Too expensive to maintain, right? So the LIS is running on HPC. Now, they will be moving to the cloud, right? But again, to us, it doesn't matter. We're building an interface to them, okay? And again, LIS could runs weeks? It's not like interactive run, right? So the other part about our digital twin we also have to think about is the limitation and constraints, right? Requirement on each system. Some system could be rapidly respond and give you a result like in the fractions of a second. Some system could take weeks to run before you get a result, right? So you have to think about how to plan, manage the jobs and interaction between the systems. So the other model that we're working on, this is actually worked through one of the JPL research scientists, and this is really for the river model for calculating the river discharge, right? The software is actually developed with Fortran 90. I think it's 90, yeah. And then using MPI, which is fine. I teach an MPI class, which is cool, right? But the question is, how do you run this? This one actually runs really fast. You could run it on your laptop if you want to, right? Or you can run it in a cluster if you want. We're in the process of moving this to the cloud because the research scientists said they really want this thing to be in turnkey, running on the serverless capabilities. This research scientist is really up to date with the technology, so I like that. And so we run this on-prem, but we are moving to an Amazon environment. But we also built in the whole DevOps capability to automate generate, creating the container, deploy the container. But the other part that we're working with Langley is pulling the other value-added meteorological data. And Langley actually got some pretty fancy cloud-based solutions. I learned a lot just by working with these guys. They have a lot of stuff on ARDs already. Surprisingly, it was like, cool. So this actually fits into LIS as part of the simulations. So for the French side, again, they took the flood ML capability that we started with the French about 2 years ago, which is a machine learning for predicting floods. They expanded to build on to create flood risks for the French region. Okay, so that's cool. So what we're gonna do is that we're gonna try to turn that into a service for the French side. We're gonna formulate, establish interface between the systems, so it'll be service-to-service interface. And that when we detect a potential flood, right, one of my model, let's say we detect there might be a flood in this region, we can actually dynamically acquire the French side, say, hey, can you generate a risk map on this area to see what are there any infrastructures? Are there human impact if this kind of flood is happening in that region, right? That's the kind of thing that we want to see, right? So that's the part that they're specialty on, and we want to leverage that. And on top of that, the French side, they are computing very high resolution Sentinel imaging processing capability on their end, the huge HPC. Why can we ask them subset that region? Can you just generate the images for that location? So we have the subsurface measurement on the discharge. We have the measurement of the depth, right? And now we have the aerial visual about the extents. Are there changes, right? Now we have the whole picture, right? So that's the whole point about complete solutions. The other part that we also want to demonstrate is that can we pull in real-time IoT measurements? So the French region, they're installing this advanced observation camera right around all the French regions, the rivers. You can tap to the system, do standard web service calls and get live feed of the data. So that's not just the measurement, but it's also getting pictures. Okay, so we want to be able to demonstrate that capability. So finally, the actionable prediction, that's the big one, where you want to not just generate some plots, but what do we need to do? Give me some options, right? Or can we dispatch additional satellites or or ground assets? Are there river gauges that we should pull the data in, right? That's the kind of question we want to bring, that we have the system being able to drive itself. So this work was built on the prior work since 2017. It was work that was done about 2 years ago. We published it to AGU to did the prediction for Mississippi River. And we built the ML in the Steel, Missouri area. And we were able to dispatch to the French side and ask for the Sentinel-1A visual. But on top of that, they built a capability on their end to analyze the image to compute the extent on the image. So now, not just the picture, now I also get the time series on their extent that they picked up through aerial observations. So this work, again, this is only about 6 months into the project. It's a 2 years project that we're building. We plan to also adapt this technology for the air quality work that you're going to hear about at 4 o'clock. But for this case, we selected 3 use cases. We continue building on the Mississippi River. There's a list of relevant data sets and models and also region that we're focusing on. There's also the French Guiana River. This is again, very devastating flood just early this year. And they're really interested in doing more analysis on that end, right? So we want to pull the data in from their sensor, which is different than the USGS data that we've been pulling in. We're going to be pulling some of the Sentinel observation and also leveraging some of the flood risk map. But the nice thing about also the French side is that they're partnering with a commercial company who's doing infrastructure data. So we want to be able to see, can we overlay the flood risk with populations and infrastructure data around the side next to the river. Now we actually have a potential a story to tell to the decision maker, like what the possible impact or cost. And the Red River is actually was a use case selected for the CEOS disaster cluster about a couple of years ago. This is actually right close to the Canadian border. So we want to be able to say, hey, they've done some imaging analysis at CEOS a couple of years ago. Can we do better? Now that we have 2 agencies, we got all the bunch of NASA public data. Now we can bring in some ground-based data. Can we do even better analysis on the Red River? So that's when it's actually on the CEOS. Now they actually tracking it. So initial work, we already onboarded a couple of these satellite and in situ measurements to the cloud. We were able to generate time series analysis and doing comparison between correlating the satellite and the in situ measurements interactively. Remember, I talked about federation, right? We can also talk to other instances of a related hydrology system that already has the same software stack, so we don't have to replicate their data in our platform. We can just leverage, just do another remote call and compare their result with ours. So that's the whole point when we try to build a community. We also have a solution to do generate tile WMS capability like Gibbs. But we can think about it, generate analysis, plots, predictions. Now you can pull in the tile WMS capability right next to your analysis. Now you have the pictures with the plots all next to each other in your notebook. That's what we're building, right? So we also just recently onboarded the LIS data. We can recreate the entire simulation outputs, right? Right in the middle using the tile WMS capability on the Jupyter Notebook platform. Right, this is just testing all the key components. So again, we started this as for those of you who know me, right? I'm very involved in open source, right? Been working on this for like 2 decades. We actually manage an Apache project, right? So this work, because we're working with another foreign agency, we actually give us the opportunity to engage a broader community. Right, so we are engaging the CEOS, we're engaging the GEO and the UN communities, and we're also working with the OGC, right, on this. The whole idea here is everybody talks about digital twin, but everybody have a different view about it. And I think Ryan's going to talk about later. It's like What's the specification? Can we formalize this? Well, we have a real opportunity here, right? As a community, USIP, should have a major role in this, is define what's the standard specification on a digital twin. What's the goal? Interoperability, right? We can't own, I don't think NASA can build one digital twin. It has to be a community effort. We have lots of models that has already been supported by community. We have lots of data that's outside NASA, outside NOAA, right? They ever talk about NFS, right? Talking about the academic environment. So we want to be able to create this kind of federated architecture that enable us to build the Earth system digital twin. So that's the part. We're continue engaging in partnership with everything we build is open source to Apache Foundations. So sign up for ApacheCon. We're going to be having a talk. We actually invited, our paper got accepted, invited to keep oral in ApacheCon in October. Okay, and we continue sharing our recipes, making the notebooks available, making our source code available. Point, because I know I'm not smart enough, my people are not smart enough. We need the community to validate, but also we need the community to help us improve the system. Okay, last slide. So in summary, right, it is really, the architecture is to integrate existing data and analysis. It's not just try to replicate everything that we already done. I think we have valuable investments already done over many years, NOAA, NASA, and all the community, right? How do we create these bridges across all the systems so that we can create a digital twin architecture? And again, we're using water resources as an example. Well, last time I checked, Earth is not just about water resources, right? So how do we create a more completely digital twin of representation of Earth? You need to continue to grow that architecture, expand that. My vision is looking at a triangle, okay? From generalization to specializations, okay? Generalization means you have a high-level API that you can talk to the system. You have a generalized metadata model. Specialization, there's the special things for every single missions, every single data set, right? You talk to David Moroney in the back, ASCAT data, it's like there's 2 parameters you have to pull in. A U and a V, it's like, who knows? You can just drop one array and you're done, right? So that's specialization. So you have to be able to create a generalized API, generalized architecture, but be able to extend to support these specialized capability. But the key here, our architecture has to be sustainable. You can't just say, well, go run with the Jupyter Notebook. How much is it going to cost me, right? It has to be sustainable, affordable. Can I continue to onboard data? Do I have to train an army of people to maintain this thing? I hope not, right? It has to be portable, so it cannot be Amazon happy only. I know there's people like, what? It has to be portable and extensible, so it's not just one-off, right? I shared before some of the system I designed for the Mars Pathfinder, 1997, kind of dating myself, is still being extended to the new Mars missions. That's the kind of thing that I'm talking about. It has to be federated, so it's not one big cloud, one big HPC, or one big GPU, right? It has to federated leverage what people have been doing, right? Building those bridges. So that's why the formal specification is so important, okay? And agility and resiliency, I think I talked about that already, so, okay. Thank you. I went over 9 minutes. That was awesome. Let me just exit this little thing. Should be good to go.
Use the arrow keys.
Yeah.
Awesome. Thanks, Jake. So thank you, Thomas. I'm very grateful for your talk, and I thought it was a great introduction. to talking about, what this idea is, and maybe a general solution for it in terms of specification. So that's what I'll be talking about, and then I'll try to leave enough time, a significant amount of time, to ask Thomas and myself questions. Our shared vision is, my motivation in getting into earth science is this ability to, grab data that I want and build models of things to answer questions. And I'm sure it's a shared vision for everybody. This picture is, or this image comes from the ESA, who's also working on digital twin, a different approach to it. So, we're all kind of working towards this target here, and like Thomas said, there is, a definition of digital twin that we're working off of. And let me see if I added this to my notes here. What I have is a comprehensive and confident current and shared understanding of the Earth system that's broadly available for democratic decisional use. That's my own summary, but we'll see if the definition's in here somewhere. So in this talk, try to keep it really high level and avoid getting into detail. I'm a technical person. I tend to get into really technical things. So, let's keep it high level. So I'll just describe the spec, and then we'll try to illustrate it. Okay, so a framework that implements this spec is going to be capable of supporting management of a contextually rich, user-driven, readily accessible, easily manageable, entirely flexible model of the Earth system that spans its life cycle, updates from real-time data of wide variety and source, and supports making, storing, justifying, and publishing fully traceable decisions made using machine learning, simulation, reasoning, and other process techniques. There's that definition I was looking for. So I added this kind of late, but I wanted to tie in two of the themes of the plenary today. Can we manage and merge the concepts of HPC and holistic platform capabilities that were part of the first talk, some of the work that CMU is doing in Pittsburgh, and then merge that with the concept of self-ownership, self-contextualization, unlocking the wisdom of many. So, towards that goal, there are a lot of approaches to digital twins going on. The planetary computer, NVIDIA is working on something. ESA is taking a data cube approach. But can we look at it, as Thomas said, in a federated way? Can we use the wisdom of the many? So that's what we are approaching this problem as, is an interoperable approach to digital twin Earth. So, it's a system of systems. We're trying to measure, understand, and explain the Earth. And I propose that, data is fundamentally interoperable due to all the scientific frameworks, the ontologies, the lexicons, the thesauri, the ways of thinking and understanding that have been developed. But most of these interoperability efforts fail. And why? And my hypothesis is that, that at the root of this is Conway's law, which says that any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. And here are some examples of different communication structures. So all this to say, why have we failed in the past is because we're trying to push something onto pre-existing structure, and it just isn't coherent. And this kind of summarizes what the promise of the digital twins that we see is all just basically enabling decisions. So data is only useful in the context of someone's quest for a decision. And we can use a digital twin based on real-time data and all other types of derived data to do advanced analytics and share data to make decisions of all types and all viewpoints. And the word viewpoints is kind of a key word here. And we want to enable decision diversity. So, I want to be able to enable decisions about acid mine drainage and streams, or, where to put my sail drones, or, did this person really get hail damage on their car, or, are we likely to see a lot of hail damage on the car, or is this Tennessee Valley Authority dam working at capacity? Can we reduce that sort of thing? So what I propose here is we need to improve wisdom from combined knowledge. So let's say I'm NOAA and I have a precipitation data set stream, and I have this normalization model, and I create a full precipitation model that feeds all sorts of decisions. My data set could be made better if I was to take all these state Department of Environmental Quality and that sort of agency data to do more localized sensor analysis. And if I was able to combine those and give them weights and say, I'm this confident about this data set and this confident about this other data set, and then combine them in an online model, I can improve my precipitation model. I can even create, multiple versions of that, and people can pick and choose, which maybe they're more confident about. So downstream decision makers. So this interoperability of viewpoints, is a really rich idea. So it's, taking one data set or one data stream. There are a lot of decisions that can be made about that, all sorts of interested people with different viewpoints, and some of them are listed here. So this all is in a formal spec that I shared with the session. So I invite people, it's in draft now, to become reviewers, but essentially derive these 4 axioms. As we propose that organizations and individuals of all sorts contribute to study the Earth system in all sorts of ways, to answer all sorts of questions and make all sorts of decisions for all sorts of reasons that are meaningful to all sorts of other users. Users might greatly improve their own decision-making confidence, et cetera, due to improved model capability via shared representation. Achieving a shared representation of users is limited by communication interfaces. And issues with communication interfaces, we can define those and address those in terms of what the GEO classified in terms of interoperability. So this is just a restatement of that in terms of the fundamental context questions. But you can see sort of the idea is this federated idea of a lot of people using the system. So let's get into implementation. This kind of simplifies things a bit, but how we approach this is as a framework developer, not a user yet, but just somebody who's building, a digital twin framework to support a digital twin Earth. The foundation of all this is model-based systems engineering. So we need this to be model-based, right? Without a model, we have no control. And then the model itself bases itself on syntactic, schematic, semantic, and legal interoperabilities. Each of one is addressed. Then we apply our functional requirements as a validator, which gives us our digital twin Earth framework. And then, key to what Thomas was saying too is this idea of a framework API, right? We're deriving and we're producing essentially a portal to use this framework. The digital twin Earth itself is just kind of, in our heads, or, what can be accessed by this API, right? And within that digital twin Earth, we're supporting shared knowledge and shared wisdom. So once we're in the digital twin Earth as a user, it's for users, they might not care about all this stuff. Maybe it's nice to know, but as far as they know, they have an API, and they can access and produce shared knowledge. and ultimately share decisions, which can also be shared within the framework. So the first thing we want to do is, look at syntactic interoperability and break our system down, or break our user systems down in terms of processes. So this is fundamentally a process framework, right? A user system can be broken down into process. Process is a space-complete dimension on itself. So you can imagine we have all these processes, these independent processes, and then we can start making bridges, making links between processes. And that's the foundation of syntactic interoperability. And a couple of years ago, I released a library called Message API, which kind of proved this concept in practice. So we have a process which is well structured in terms of a model, and then we talk to those processes through sessions, and each session's well structured, request and response, and requests are in terms of records and conditions, and we have a life cycle that we go through. And the key here is that I have a well-defined data model that can be described purely in data. So I can pass a full request, right, a full session to the API. So the API itself is space complete and stable, which is really important in a federated environment, because if my API changes, then I have to change it for everybody, right? So you can read through the spec, but I've tried to put the requirements into plain English here, but here are some of the rules for doing it. And we have to match this up with also the behaviors we need to support as a digital twin earth, which include online models, streaming, concurrent sessions, late binding, which is really important, and everything passing through this API. And we also have some recommendations. So now moving a little bit beyond syntactic interoperability, we can look at schematic interoperability. And to do that, we take our process, which we defined for syntactics, and we break that down into these classified tasks. And a classified task is, itself really a process, but it has a purpose. And every process can be described as inputs, identity, transformation, which I have as contextual transformation, just to describe that better, and outputs. Okay, and we have rules about how these things can link together. Internally, they all look pretty much the same. They take input, they do computing with some late-binded user logic, and then they produce an output. This late-binded user logic is another key to this, in the fact that the model itself should support any user logic. So in Thomas's world, we can go and call a service within a task. But the schematic part, the schematic interoperability part, is we can stereotype the processing of fields, right? We can stereotype everything into a flat map of fields that are key value pairs. And that's the key to this schematic interoperability. We can have tasks that do anything, talk to anywhere, at anybody's machine, and they can specify that. And they can specify construction time parameters for when I deploy my process, and then runtime parameters for when they receive data. And all we have to do then is know what to provide in the immediate record, and then what that feeds out. So the other important part of this that I didn't hit on was in a task, you can also represent it as what it produces, or what it produces and how it produced it. And that coupling is fundamental too. So every task takes some input map. It's going to do some computation according to key value pairs on that input map. It's going to produce some output map according to some schema in its message, and then we can use that to fill in arbitrarily structured structured things in persistence. So going back to the message API spec, this was, kind of just an extension. So we can pass in that full session telling a processor exactly what to do in terms of fields and conditions, where every field has an ID, a type, value, whether it's required, etc. So here's an example of that. This is obviously just an example. It's not part of the spec, but you can see here we have flat fields and conditions, and we go through some different types of processes. Here we have transformation, and then a connection to an endpoint, which is an output. So again, here are some rules and recommendations for schemas. So now moving on to the more interesting realm of semantic interoperability. And here's where we want to introduce the concept of fuzzy interoperability. So we're all familiar, I think, or many of us, with ontologies, domain-specific ontologies. But this concept of fuzzy interoperability, which I found to be best described in this ISO standard developed by my friend Thomas Beal of OpenAIRE, deals with the concept of a reference model, which can provide building blocks. They're generic classes and structures, and then you can use those to construct images of what you understand your domain to be based on those reference model building blocks into these things called archetypes. So it's just like if you ever played with Legos, it's the same thing. So archetypes are just human understandable, human labeled, empty structures based on a reference model. And if we implement that in something like RDF, then we can do class-based searches, we can do label-based searches. We really just have complete freedom. And here are some reference model-based ontologies that I think would work. We've looked at many of these. Prove, even just basic context questions. The 13606 OpenAIRE standard, and OAI ORE. For our purposes, we found something that worked a little better, but I think any one of these would work, right? It has to be generic enough to apply the concept of fuzzy interoperability to create processes, task output structures, as human labeled configurations of these Lego blocks. And then we can define all fundamental concepts as templates, and processes hold templates. It's getting a little bit technical. But essentially they allow the support of managed open-ended context within transformation. So the other question is, that's great and all, but how does this really support, all my specific domain concept? And the answer is no, and it's not meant to, right? There has to be, in transformations and in endpoints, communicating sequential processes tells us that a vocabulary and alphabet of a process can change. So the transformation alphabet needs to be able to be contextualized within this, and that's another key point here. So to handle the issue of scalability, in a system like this, we can isolate all these different concepts within their own space, and RDF provides a very easy way of doing that with that fourth graph dimension, which is the graph itself. But essentially, we can create isolated subgraphs of this thing, and then we can search against things that match. Does anything share my idea of a structure? Is somebody else using my structure? Or we can even search against descriptions, content, instances. Can be separated. So here are some rules for semantic interoperability. There are quite a few of these, and a recommendation. And then the fourth, or the highest level of interoperability, is this concept of legal interoperability. And what the framework spec says is, any process in the system, if I want to be using it, I don't necessarily have to let anybody else use my processes. So it has to answer these two questions. Can I, as another user of the DTE, access this? And then if I can, if I'm allowed, how do I, as an authorized user, what schema do I need to provide to get something like a token for executing your process? So that ties really well, I think, into the concept of plenary and cell phone data, right? So all that said, it's a little long to go through a spec, but we have been implementing this. Okay, so this spec is being implemented as the archive and access part of NOAA's next generation Common Cloud framework. So why did we take this approach? Is the archive and access service is unique in this Common Cloud framework, and that it sees and is responsible for disseminating all of NOAA's data, right? Not just satellite data. You remember when big data was a buzzword years ago, we want to handle and we have to see all types and variety of data. We are going by the SAFE, the Scaled Agile framework as our governance model. So, we're only implementing things as the business requirements dictate. But as a composable spec, we can do that as long as we have the basic structure. And this thing is called the Virtual Archive Information Package. So, particulars of the implementation, we use the OAIS reference model as our base ontology, specifically only the information object and information package parts of it. We're obviously driving through API in this concept called archetypes, and we're using the semantic web. So, looking a bit to understand better this concept of fuzzy interoperability, here's the basic building block of our system. It's an information object. And the really interesting thing about this is, this is in RDF. It says data is just bits, and it's a familiar standard to a lot of people. But I found in implementing that many people don't understand it completely. What it also says is these representation networks are required for fully describing this data. And each one of these representation networks, which are either structural, semantic, or other, are also in turn representation networks. This provides the ability of recursion, so I can richly create these dynamic networks in pure data. And then here's the other concept that we needed, was just the package, which provides this rich context in terms of preservation, packaging, and description, okay, which are also information objects. So we took this information object package and access aid concepts from OAIS. We called data just bits. Just bits allowed contextualization. Packages provide well understood context structure. We also implement this idea of knowledge of data in the VAIP, right? Our knowledge network only cares about knowing that you have data, knowing the data exists, and knowing how it's contextualized. The model also allows multiple avenues of semantic interoperability. Like I said, through fuzzy interoperability and this concept of archetypes, but we also have template-wide values we can search against. And then we have representation network links to values and descriptions. So here's the basic concept of operations. So you can see this kind of generalizes the concept of a community-owned system. We put data in as an input. We ingest it and turn it into units, which are identify layers, like identify processes. And then these identity layers can be turned into arbitrary collections and collections and collections of collections, which can hold arbitrary transformation vocabularies. So here's an actual archetype, and this is our process archetype. which holds a link to the workflow configuration, describes it. It holds a link to downstream processes. Here's an example of an identity layer. So one of the interesting things that we can do with this is we have this concept called the granule at NCEI. And a lot of our sub-organizations use this concept. However, they've all historically called the granule, it means something different. Here we can encode those rules about what a granule is to you or to me, and then I can search against both in a class-based way. And we can start to normalize over time. And here's just a better view of identity. And then here's what I was talking about in terms of custom alphabet support. So here's something called an AIC, which in our general solution language, this is a context transformation, right? So OASE actually provides this same idea. It's called an archival information collection, and it has this thing called a membership. And here you can see it implemented. And in this membership description, so say I have an identity that produces some unique thing, some unique piece of data, I can attach it to this context task, which has it's a membership description of a person and defines that person and uses the friend of a friend ontology. And all that information that it does all that it's contextualized that way is now encoded in data, and I can go ahead and search on that. And here's the last piece of the puzzle, which is the record of endpoint delivery. So I can deliver to repositories, to any access aid, right? Any tool in terms of its own schema, and still record knowledge that I delivered it there. This is the implementation that we've done of the tasks. You can see we have various workflows for each. We have identity, contextualization, and data delivery. And then here's a better view of a process. So here's a process is just a connection of these various tasks arranged in a way according to the rules that we've provided. And then here is handling of versioning, which is a key requirement for supporting online machine learning models, as well as simulations. I need to version my process itself, so I can rerun the process, so I can know about changes to the process. And that's all handled, as part of an identity layer, right? It's a self-contained and self-describing spec. Here are just some examples of relationships of identity units and how they're contextualized into an isolated context within a context transformation layer. And then here's the vision of how this would look to a user, right? So I've gone through in a lot of detail on how I would build this thing, but as far as users are concerned, all they have is an API, and that API, because it's based on a static data model, they have a static API that they can use. And then we can build things like interfaces and things on top of that API. And then just here's an example of how it would look in code, right? I can create processes, I can create loose storage structures, I can attach storage structures to processes, I can deploy processes, I can query processes, etc. And based on our federated system of membership, based on our federated system of users of this thing, we can have users that are dedicated to making specific collections, searchable, things like that. And here are some references for later use. So that's all I have. So now I think we'll ask Thomas to come back up and see if there's any questions. I hope there.
Mike?
Test.
So you caught me with the word digital twin, which seems to be a modern buzzword, but it seems to be just kind of repackaging what we might know of as weather forecasting or Earth observation. So can you speak a little bit about, this whole concept of digital twin? I've seen it also in the architecture, engineering, and construction field, building models, a digital representation of a real building. So are you just trying to get on that bandwagon for all the technology that's going to come from those other industries that are using the digital twin terminology?
I'll take this first and maybe you can chime in. I see that connection with the weather forecasting a lot, at least within our domain. Have you seen this outside of the weather forecasting domain? Besides within digital twins?
Well, I've seen it in OGC contexts and also in the architecture engineering, from Dassault and Autodesk are using that as kind of a buzzword to talk about their technology and to sell product.
Okay, yeah.
So are you doing the same thing?
Yeah, I was in ESA and I couldn't find that digital twin baseball cap there. Definitely not, right? It was an idea that came to me when I was meeting with the AIST program. And I'm pretty sure it was a buzzword started off when they meet with the ESA, right? But as a professional computer scientist, I look at this as an opportunity to formalizing an architecture that connects all the different information informatic solution or investment that agencies, organizations have invested in. At least from NASA point of view, I see that there's still a lot of stovepipe in programs and focusing on I'm doing model only, I'm doing ML AI only, right? And we're doing some data access only, right? How do you make all these things work together, right? That's the point. And I think, but the goal is that you try to create an environment that truly represent what do we know about our environment at the current state, but based on the environment that we have or information we gather, what kind of inference that we can draw from it that can help us to be smarter about what the next action we can take, right? So definitely not in the business of trying to cash in because JPL not paying me enough. So.
Again, kind of to riff on that a little bit, I think the flexibility is something that probably isn't seen in forecasting, but also, if I support all these different viewpoints or about, the quality of some model output, and I have a security viewpoint, and then maybe I have 3 different security officers looking at this and they all have their own model. I, as a downstream user, can look at and see, do I actually accept any of the conclusions made by, or do I respect any of these specific security people's judgment? And it kind of opens it up to that use-based, context, which, have we seen anything like that? I haven't, so.
All right, so first I want to apologize, Ryan, because I'm about to set you up, okay? But I really like the slide on the Conway's Law, okay? And so my question is, do you think that if we're successful here, we can actually create an inverse Conway maneuver and have this horizontal communication way of working together, like as you were just describing, actually then drive change within the organization so that it doesn't mimic the structure of Conway's Law?
This is for me.
Yeah, well, I'm setting you up.
You really have to slide, man.
But it could be either one. But
I mean, so everything is a structure, even if you say you're outside of structure. So yeah, I guess we're constructing a meta structure, but it's a democratic structure. So if nobody uses it, then it doesn't exist, right? So that was, that is kind of the worry is, in spending all this time thinking about stuff like this and building it, do we actually have a user community? But, I'm lucky enough to have people that have to give their data to me. So, I don't really have to worry about that, but I think it's a valid, thought there, so.
Thanks for the talk, Ryan. That was excellent. I'm curious, with the idea of archetypes, is the idea that there can be infinite archetypes, or is there a sweet spot where they should be limited and carefully thought out to sort of keep things efficient?
Yeah, thanks for the question. This is actually the best question, to me, about archetypes. But I think, again, we can go back to, let's start out and let people build archetypes. They're supposed to be cheap, but let's, if people start using this concept, at NOAA, and then if we, in a broader sense, like OpenEHR has revolutionized healthcare in this way. I think we can start doing analysis. It's all pure data. We can say, who's using this? We can go say, why are you using this different shape when you can use this other person's? We've never had that visibility into that before. We can start standardizing. We can use governance models to I think, manage that.
Well, thank you for the great session. In fact, the first introduction of different use cases to get us onto this topic, digital twins, what does it really mean? And then you came up with architecture to touch on almost all the infrastructure side. So we know that digital twin is kind of a buzzword. Everybody's talking about it. It's so broad. What's your thinking about, could we have digital twins for everything, or we should have some kind of level of balance? For example, we can have that for flooding, but could we have digital twins for our cars? Or let's see, on the air quality side, could we have a digital twin for people air sensors? And so that's kind of a balance between the broadness and the best practices. And also going into that, would the architecture discussion apply to both, or how generalized we could have the architecture, how specific we could have that for each use case? And finally, what do you both think that's the most challenging part in terms of technology for digital twins, and how that should be addressed? Thank you.
So I'm going to try to take a stab at this. So the intent of the digital twin is very different. First of all, yeah, I know the term's overloaded. We should call it the thing, and just be done with it. But again, I guess we could use that as a way to easily communicate, right? We in big in taxonomy, right? Use the same term. But what we see the digital twin is not, you could deploy as a domain-specific digital twin, which is definitely possible to do. But for Earth system digital twin, I see that as a way, as a community way to expand. Last time I checked, the Earth systems is connected, is interconnected. There's forces there, there's a cause and effects, right? Actually, is the architecture is a solution that require evolutions and evolving over time, expanding to cover. So we have air quality, you might have flood. Somehow there will be some linkage between the two. But the other things that I see the digital twin, I go back to my other comment earlier, where we have very specific investment on technology, at least from NASA, and I'm pretty sure it's the same thing with other organizations. Having digital twin connecting these things together, or technology that enabling connecting observation, model predictions, and being agile, also allow us to identify if there are any gaps. I spent a lot of time talking to a scientist who just refused, say, we just don't have enough data, we just don't have science for this. I go, okay, I get it. But if you build this together, now you know what are the gaps. that also helps the organization to think about what's the next investment should be. What is the next mission that we should build, right? I mean, that's another opportunity, but without connecting these pieces, having something like digital twin, you still don't know. Everybody is happy building the ML model, but the problem is that how many of them actually get to the productions, right? But being able to connect them, now you're actually solving a real problem. You're looking at a real domain, and you also would see that where there are any gaps in our solution, right? So I see some of that as well, but the solution is built for, could be deployed for domain-specific applications, but also could be expanded to global, right? So.
So this is the proverbial dumb question, but is there any synergy going on between these efforts and the history of Earth systems modeling, that started up more like 20 years ago, and kind of coupling models, mostly focused on climate forecasting? I'm just wondering whether there's any connection to that history of Earth systems modeling work, which I mean, there's still a lot of people doing that, right? They're not calling it digital twin, but thanks.
So I'm not familiar with that work. Are there any synergies? Probably. I think it's important to stick with definition and always base things on definition. And one of the definitions of a digital twin is through its history. So a product through its history. If we were able to connect with that organization and look at what they're doing, we have started working with the OKN, the Open Knowledge Network, through the National Science Foundation, and who's doing a lot of knowledge modeling in ontologies, which through the spec, fits really well. Looking for collaboration. So yeah, if you have more information on that, and who to talk to, please share.
Yeah, so I think the vision that we have for the Earth system digital twin is very tied back to the earlier, the keynote speaker about Iron Man, right? Actually, that was the same analogy my program office was giving us. Like, can we get into a system where we can actually play out a scenario and submit to the digital twin and give us the predictions and tell us what to do next? I think this, including identify the right models or selection of different kind of models that you want to integrate, or how to connect these models together. But also identify the other part that I did not talk about is how do we address the uncertainties, right? In some of these predictions, every prediction has uncertainties. That's another thing that we need to be quantified as well. So when you play out your scenario, part of that, we also have to present the user, well, what's the likelihoods, where the uncertainty we're dealing with. So I think the purpose is of creating an environment where things can be interoperable much easily, but there's a sustainable end-to-end solutions from observation all the way to predictions. That's the goal. Now, there must be historical connections, and I'm sure there are, but I guess we're looking for this opportunity to formalize that. Speechless. 5 minutes.
Well, we'll be here all week, so, well, I will. I don't know about Thomas. He has another presentation or something, but, did you want to talk about your other session, or he's doing another equality session today. And the other thing I wanted to mention is, if you'd like to be working on something like this, we are looking for people at NCEI. We have some job postings, so please come talk to me. I can, or Ken, I see Ken out there, and be happy to discuss. So thanks.
So the other part that I want to point out, I was talking to Ryan about this, is if there enough interest in the community to start putting together more like a cluster in ESIP, right? As I mentioned in my talk, digital twins cannot be just solved by one organization, cannot be solved by just one company. It's really a community effort, right? And we are in the process of formalizing the specifications. I think having a community like ESIP supports actually will really help to formalize that. Again, whatever specification that we are putting together, at least do my project, we are going to be presenting that to the CIOs and the GOs and the UN. So that's one of the things that we talk about to our last conversation, is there's enough interest to form a cluster at ESIP for this effort. So is that a sign up or is that a question?
If you don't mind, a related shameless plug with NOAA. Also, we have a virtual workshop. Sorry, it's not in person again yet this year. It's the 4th annual NOAA AI workshop. And one of the things will be on interoperable digital twin systems.
Yes, so, I signed up for it.
Awesome, yeah. So you can go to noaa.gov/AI if you have any interest.
Great.
Thank you. Yeah, and great session, thank you.
Actually, I have a question. So to improve product performance, collecting observation data are very important, like in situ data. Right now, they are scattered around the world. Can you digital twin, collect, or let user submit this data, and get a credit, in order to improve, Since I'm from NASA. NASA is basically on a global scale, and and also some countries, they refuse to send out the data, share the data. That's a big problem. Is there any thoughts?
I don't have some thoughts, but you can.
Okay. Well, first of all, digital twin is not the magic bullet, just like the cloud, right? We are pulling in situ data, right? As long as there's an interface being formalized, right, documented, right? We're not going to come and tell you that you can drop any data to our system. We'll make magic out of it. But again, there will be places that we don't have data. This is where we identify gaps, right? But what we are, at least for my work, right, we're pushing for is be more agile, right? Yes, we couldn't get some of the ground data, but are we able to get any aerial observation? Are there any airborne data? Are there commercial data that we might be able to tap into that we can actually fill in some of the blanks, right? That's the kind of thing that we want to be a little bit more agile and in terms of what data to pull in. But I'm sure there will be places that we find that there won't be any data, right? But the whole point is creating an architecture that actually being able to do that. But this doesn't do away with your ICD, right? I came from the DAG, right? Your interface control document. You still have to formalize the interface. Some of them give you 2 columns of numbers. Some of them give you an SCDF file. Some of the sensors are terrible, right? And I use some of that, right? And just say, forget it, don't even use that sensor. So we need to start building that knowledge too, so that we don't avoid wasting time pulling some of the best sensor data as well. So.
Yeah, maybe more on the theory side, but I think, as part of the spec, that's what that context transformation can do for you, right? You can define a membership or a transformation vocabulary that is able to contain knowledge of various sources that are globally distributed, and then provide you information on, is it accessible? What is accessible, without actually having to move the data at first. You don't have to move data. You just have to know about the data at first. And then if you want to use the data, you could do some lazy evaluation of that data in an endpoint. You can collect the data if you're a user and you're legally interoperably allowed to do so. So that's the other aspect.
Somebody said they couldn't hear me. All right. Yeah, if we had, because I completely agree with you about moving data, please don't get me started on that, but if we had a rubric that not just said how like archivable is the data, but how interoperable it is, how is it compatible for your use, that would then tell them whether or not they could even use it in their model and start running with it and contributing, so, with that whole matrix that you were describing earlier. So I think that's something that's a key force multiplier that can really help make decisions.
Yeah, that will require a lot of work, right? I mean, if you ever go to PODAS, search for SST, you have 256 sea surface temperature products. The first question our user has been for is, which one should I use? They all level 3.
Yeah,
right?
this is definitely not a one-person task, for sure. This is definitely something that needs to be collaborated across multiple agencies, across multiple disciplines, because there's no way one person could create every single type of rubric that would be needed to determine whether or not it's usable. So I completely 100% agree with you, but we need to expand that mind thought of having multiple rubrics to tell you whether or not the data is compatible or interoperable and ready and all that good stuff.
Yeah, I know we're out of time, Dave, but I think that's, the whole point of, contextual control over quality control, right? So maybe you're just driving that point home, but, I can create my own space and say, does this satisfy, or, NCAI can create a rubric like this and we can just attach that as a collection to the output of different data streams and then run it through a model that knows how to calculate that, maybe different models. And then we can search and say, who's making decisions based on this data set? And maybe even, was that a good decision? And then maybe that's how we can say, yeah, this is the sea surface temperature data set I should use because it's been used in good decisions. So.
Okay, I need to run. All right. Thanks a lot.
Thanks, everybody. Take care.